Good morning, everyone. So you guys, thank you for being here so bright and early. The first talk is always a fun one to start off with, but I'm really glad you're here, and I'm really excited to tell you about what my background in research is on, which is actually quantum computing. So I actually didn't know anything about ML before I came to this conference last year, and now I do it for my job. so can you. Click. Oh, no. There we go. Okay, cool. Yeah, so just as a kind of a quick introduction, if you were here yesterday, I do a lot of authoring in my spare time. I'm really passionate about making science and STEM accessible for all ages and across all topics. So I've done some baby books, and actually just today, you guys are the very first group I get to talk to. Our textbook went live last night, so I'm so excited. My partner Chris Grenade and I have been working on an very focused on entry-level sort of math and programming skill textbook to teach how to program for a quantum computer, which you guys will get to kind of see some of the demo stuff for that here. So first part, what can we expect from the field of quantum computing? This is kind of like some of the other talks, an interactive talk, so just shout out things that you may have heard about quantum computing. Qubits, all right, cool. Noise, all right. Anything else? Minecraft? Oh, time travel, yes. Ooh, that's a good one. Encryption. Speed, okay, cool. These are all very good things. Since Google happens to know that I do quantum computing, it likes to suggest articles that I might be interested in. So I get all these headlines all the time that are like, quantum physics can help explain much of the world's suffering, quantum computing could put a stop to traffic jams, what's the other one that's good here? Whoops. Physicists race to demystify Einstein's spooky science. So the fun fact is, one of these here is actually not crazy. Weirdly, it is the braiding might be a key to using time crystals in quantum computing, which really does sound not super legit, but I actually promise you, part of the problem here is that physicists really like whimsical naming schemes, which is great for them and their community, but when it comes time to actually communicate the results to the broader community, it kind of can lead to some confusion and misnomers. So what is a quantum computer anyway? Sorry, I'm going to fix this real quick. Well, here's a picture of one, or rather a diagram. Really what a quantum computer is going to be like is kind of like GPUs or, since we're at an ML conference, TPUs or tensor processing units. Quantum computers are not going to replace your regular laptop. You're not going to have one at home. Like, kind of think of some of how the early model of computing was in that, you know, there was universities that actually hosted machines and you could remote in for time. It's probably, as far as we can see, going to be a very similar model for quantum computing because the big limitation is you have to keep the hardware in a fridge. And not just like your regular kitchen fridge, it's a fridge that keeps it at almost absolute zero, colder than outer space. So unless any of you have one of those in your garage, likely we'll all be using cloud resources to actually remote in and use these devices. But importantly, how we actually control and interact with them looks a lot like what we're familiar with. It's just a regular program with a programming language that you run on your computer, and it handles interfacing with the actual hardware. So that's kind of what it looks like from a hardware perspective. What is different about quantum computing from an actual computing model perspective? How do you represent information on your laptop right now? Ones and zeros, right, bits, or binary bits rather. So if you need to, I mean, anything we do, you know, from C# level code eventually ends up as ones and zeros on our hard drive. And if you want to write down more than just, well, one bit of information, you could talk about a register of these bits. So that's nice. What does it look like for a quantum computer? it's going to be kind of similar, except rather than having a string of ones and zeros, we have a vector of complex numbers, which I realize sounds like kind of a big jump there. But the good news is we are actually already really, really good at doing things like multiplying matrices and vectors on classical computers. So we have kind of a lot of experience with representing data in this format. So if I wanted to maybe write an example of a quantum state that my quantum computer could have, we use this notation here called a ket, which is just this line and angle bracket. It's basically just a label for your register, just like you would label a variable like foo or something like that. So that's if you see notation like this, just know that's a label for a particular data register. And here, we have a vector for 2 qubits, which ends up being 2 to the power of 2, or 4 elements long. Excellent. So if that doesn't make sense, or you're really sleepy and your coffee hasn't kicked in yet, I'm going to give you the too long didn't read for the rest of quantum computing right here. Quantum computers are not universally faster or more powerful. It's really going to be more of like a GPU sort of use case model. So yeah, you're not going to have one at home, sadly, even though I'd really like one. The applications that are going to be exciting in the near term are not necessarily the ones hyped. So we'll talk a little bit, especially because machine learning is one of the very exciting applications for quantum computing, why the applications you might have heard of, breaking the security of all cryptography, whatnot, are not necessarily going to be here tomorrow. And most importantly, and what I am really excited to demo some stuff today, is we can actually start programming for quantum computers right now. Like, we have the software tools to write code that we can either now run on mostly simulators on our local machines, like literally on your laptop right now, you can run simulations with up to about 30 qubits, which is really exciting. But especially given that most hardware that is available is kind of on that same order, maybe a factor 2 more. But yeah, so we can actually get our hands on and start trying to understand something, because I know I'm a very experiential learner, so being an experimentalist, so like if I can actually get my hands on and try coding something and try like getting all the warning messages and error messages and forgetting all the semicolons, I actually learn better. So it's much easier to do that than just look at the math. So as I alluded to earlier, what are the applications that we might actually be able to use quantum computers for? So as someone very correctly shouted, cryptography is one, both in the aspect of breaking current classical algorithms, as well as building up new hardware for doing particular cryptographic protocols. So actually, quantum key distribution was what I focused on for my thesis. Talk to me later about that. Chemistry and material science. These are the ones that I'm really excited about. So it seems kind of weird, but the most exciting application for quantum computing is to simulate other quantum systems. Which is like, why did we even bother then? But there's actually a lot of problems that for us to classically simulate, the resources either like scale very badly or it takes really long time. So particularly in like material science to understand some chemical synthesis problems. And as an example of this, nitrogen fixation is something that Microsoft is looking at, which currently consumes about 1% to 3% of the world's energy budget, just because we don't understand how to take nitrogen out of the environment as efficiently as plants do. So whatever processes that we have to basically make fertilizer, which grow the plants that take out more nitrogen, is not very efficient. So if we could maybe understand the chemical processes which happen at the quantum level in plants, we might be able to do it better ourselves and help with global warming. So that's a really exciting application. Similarly, machine learning, which hopefully we should all be excited about here. Cool, so all right, we've gotten through the very, very abbreviated introduction to quantum computing, which makes it a lot easier to now talk about how might we be able to use quantum computers for machine learning. So as I kind of mentioned earlier, let's just dive in. Let's start looking at what a quantum program would look like and see how we might use it for ML. So as I mentioned earlier, our code for a quantum computer doesn't, like, it pretty much just looks like our regular code. You know, we have, we use operations to say what happens on our devices. So let's, yes, and to be clear, what I'm going to be demoing here is the new programming language from Microsoft called Qsharp, which is a .NET language that is a domain-specific programming language for quantum computers. So it's an entirely new language. And it focuses on a very high level of like algorithmic programming at an algorithmic level. Most of the other resources available, there's obviously lots of other toolkits from different companies like IBM, Google, Rigetti, but a lot of those are kind of more at the compiler or like a machine instruction level languages. So it's, you are actually sending kind of like opcodes or machine language to the quantum device. So you kind of have to think at a much lower level to actually say what you want the hardware to do. Here, most of the back end of Qsharp will handle translating that to whatever you need to actually send to the device. So here's kind of a model of how Qsharp works. So we will be writing our Qsharp program here, and the program is basically run by another host program, which is in C# in this case, and that handles basically compiling our program for whatever sort of target machine we want to run it on. So this is really nice because it kind of decouples our program from knowing about necessarily what hardware or what simulator we're going to use it on, which means if I write a program for my simulator, it's immediately usable on hardware as it becomes available. So we today will be running stuff on the simulator target machine on my laptop, but you can do other cool things right now with the Quantum Development Kit. You can estimate like how many resources your algorithm, so even if you can't necessarily run it, but you want to get an estimate like, is this going to take like 100 qubits or is this going to take like 20,000 to know if you should like be really excited about it and bring it to your manager right now. So you can use resource estimators as well, and hopefully hardware, as I said, hardware should be coming online soon. But yeah, so that's really cool. Let's actually take a look at it. And that's my puppy. Sweet. So one of my favorite things about Qsharp is that it actually has a Jupyter Notebook interface. So there is both an there's both Python, a Python API, as well as a way to actually directly, as you can see kind of up in the corner here, this is the logo for Qsharp. We're actually running a Qsharp kernel for this notebook, which makes, at least for me, makes it really nice that I can just kind of play around. I'm very, like, my introduction to coding and programming was basically with Jupyter Notebooks and Python, so, you know, this is kind of a very friendly environment to take a look at this stuff. So, how do we get a qubit? So basically, everything we're going to do in Qsharp that we want to be an interaction with qubits is going to be an operation. Is this big enough that people can read? Yes? Bigger? Okay. Bigify. There. Oh, no, don't scroll. Okay, cool. Right, so everything we're going to do in Qsharp to interact with qubits is going to be an operation. And so here we have an operation that's prepare qubit. We have a return type of unit. Everything in Qsharp is tuple in, tuple out, so you have to hand it, even if it's an empty box, you have to hand it that empty box, and you will get out an empty box. So yeah, and all we're going to do here is we're going to say, all right, I would like simulator, or target machine in this case. Target machine, I would like a qubit, and I would like you to tell me what you're using to keep a record of it, and then reset. So I will actually run these. And when it's done, it's taking a while to spin up the whole SDK. But you can see here what the computer is, or what the target machine is actually doing is it's keeping this kind of list of vector elements. So kind of like we saw before, this is our quantum information. Now, normally you wouldn't have access in a real system. You're not going to be able to take your qubits and say, please, can you tell me, or in some way measure them to actually get out every element in that vector. You have kind of much more limited tools to find out what's in that vector. So, but yeah, cool. And we can also do cool things like build random number generators. So with just one qubit, if we prepare it in a superposition, I will say that with the appropriate hand wavy, but that is basically just a vector with 1 over square root of 2 in, so with one qubit, that's a vector of length 2, and in both entries in that vector, it's just 1 over square root of 2. So if we do that, I'm not going to run it because my computer is being very slow, but you can see here, here we are doing a QRNG, so a quantum random number generator with some information dump out, and we can see when we prepare the qubit, it's in the 0 state. So these are the real values for each vector element, and the second column here is the complex components. So yeah, complex numbers are fun. But yeah, and here, this number is 1 over square root of 2 in decimal form. But awesome. So let's go back to our slides here. What are some quantum algorithms that you might have heard of? So Grover's algorithm is a pretty common one that allows us to actually search a list of n items in square root n steps, which actually seems really cool because normally even to just read a list on a classical computer, well, you'd have to look at every one of the n items. Here you can search for something in less steps than it even takes to look at the whole list. That's a good question. I think it's any list, but I will get back to you. So another common one that is definitely the one that gets hype cycled a lot is Shor's algorithm. This is pretty big because it actually allows us to factor factor numbers faster than in sub-exponential, or in polynomial time, rather. So right now, factoring numbers is kind of the canonical computationally hard problem that we base a lot of cryptographic protocols on. So we assume that an attacker, it would take them a really long time to try and guess what the factors for this number are. Well, that may not hold if we have quantum computers that can run this algorithm. So that's kind of where quantum cryptography comes in to actually help you build a better system that doesn't rely on that. But the caveat with this one is it's going to take some time because we need way more orders of magnitude of qubits. Like even, so for an RSA key that's like 2048, it would take at least 2048 qubits to even just put that into your quantum computer. And given we have maybe hundreds right now, and that leaves you with no qubits to actually do the operations with, yeah, you can see. And Deutsch-Jozsa, which is another interesting one that actually allows you in a single query to like a black box representing a function, you can find out something about that function without having to try like every possible input, which you would have to do classically. Or you may have to do classically. So those are like some of the like name in big lights quantum algorithms. How do you know if you should use quantum resources for your problem? Sadly, I cannot give you any hard and fast rules for this. This is a very active open area of research right now. So what I can say is some properties of problems that we do know we can get speedups on. So one example of a property your problem might have is it has a simple output. So if the question or problem you're trying to solve is like a binary output, like yes, no, or is dog, not dog, that might be a problem that actually works well for a quantum computer. Kind of like we saw before, we can't actually read out all of the elements in our vectors. That's kind of what leads to this kind of criterion, because we want to make it so that there's only one thing we have to measure in that vector, which easily maps to kind of a yes or no question. Other aspects of a problem that might be useful is if you don't have a lot of I/O, which sounds kind of bad for machine learning because generally we try to deal with lots and lots of data, lots of input to do training and inferencing, which right now is basically a limitation because we don't have a lot of physical qubits, and we can only simulate up to like maybe 30 or 40. There isn't necessarily a fundamental reason that we can't have that large input and output, other than we don't have the qubits, and we still don't actually, even in a theoretical sense, have a way to implement quantum RAM or QRAM. So basically when you do your operation, you have to load your data in, do your calculation, and measure out. You can't kind of like hold on to something and wait and use it later. So you have to kind of design everything to be done in like one shot. And lastly, problems with lots of intermediary calculations that you don't care about. So for example, the problem of factoring large numbers, like Shor's algorithm is a good example of this, because when you try to factor these numbers classically, generally what that means is you brute force, you guess a number, you find its GCD with the number that you have, and okay, now you found that information, but that wasn't what you're looking for, so you try the next factor, you try the next factor, and that's actually a lot of information you're learning, but that's not what you're interested in. And that's kind of where quantum computers can help, because quantum computers allow you to express less powerful operations. So, which seems kind of weird, but you're not, when you use Shor's algorithm to factor the large number, you're only getting the answer you actually want. You're not getting all of that additional information about the factors for everything else that you tried up until there. So that's kind of what allows it to be more powerful. But this is definitely kind of a very subtle and tricky point to try and like think about algorithmically. So building on that, asking less is more. If you could actually figure out how to do less work, it kind of does make sense that you might be able to do it faster. And given that quantum resources are at the like literal physics level fundamentally different than the magnetic bits that we use to store data now, that's kind of wherein it becomes really interesting to use them. So now let's do some machine learning. How can we apply these algorithms that we've now looked at to accelerate machine learning? I will take a good leaf out of some of the previous talks' emoji use, but I am not, we're not entirely sure. Things we do know. One, quantum machine, we do have some subroutines that actually we have found we can run faster on quantum computers, which is really exciting. So, you know, kind of, again, exactly that same model wherein you would use a TPU or a GPU to kind of accelerate part of your algorithm, and then you kind of do the rest of the cleanup and collation on your regular CPU. We have ideas of how to do that. However, most of how we would actually use those right now, we lose all of those advantages in trying to get the data in and out of the quantum computer. So, kind of a good news, bad news thing. So let me give you a couple examples, though, quick, of what algorithms we have found faster ways to do on the quantum computer. So linear least squares fitting. We had a couple talks that talked about this yesterday, but basically doing this general kind of linear algebra problem of you have a matrix A and a vector X and an answer B here, another vector B here, and you want to find out what X was that gave you B. And if the matrix is small enough and you can find this out, you just invert A and everything is happy. we know that we can do this in exponentially less time on a quantum computer. So we can do this inversion process to actually find out what x is. So as you might guess, since we saw some vectors and matrices earlier, if we just replace those vectors that were x and b before now with quantum states labeled x and b, we can do this operation. But now our answer is in the form of a quantum state. A quantum state here like this, which is a vector of complex numbers. But again, we can't just read out the register like we could classically. So we know we can do this inversion part faster, but unless there's, so how could we actually use that? We would either need to make multiple copies of this and basically measure one part of the vector each time. So hopefully either your vector is fairly small, so you make it in small dimensions, or you have to make multiple and additionally you'd have to make multiple copies, and basically as soon as you have to start making those copies, again, you blow away the advantages. So it's a little sad, but it is exciting because it is a task that we know we can't do faster on a classical computer. Another example is quantum perceptrons. So perceptrons are kind of one of the much more earlier concepts in neural networks. It's basically the individual nodes in our neural nets. You have a bunch of inputs to the perceptron that are all weighted. You do a weighted sum. You have some sort of activation function here, and you get an output. So basically just your run-of-the-mill individual node in a neural net. We can implement these on a quantum computer. So we can actually make quantum perceptrons. And I have a demo of this real quick, which I definitely won't run this one because it takes a little bit of time. But so the problem that we're doing here is I just made up a data set on angles here. So I have two classification sets, and this is kind of a plot of the arbitrary angle that I picked to be the dividing line. And we can then use, so what I'm doing here actually is I have my Qsharp file and my Qsharp code in a separate file, so I can actually still run it separately with the .NET stuff, and then also import it here. So now I'm actually, my Jupyter Notebook here is actually running Python. So I can use pandas, I can use NumPy, I can do everything that I like there, and still get access to results from Qsharp, which I find really fun because I really like pandas. It's the best. So yeah, so like here, we will import from the namespace from our Qsharp file, quantum perceptron, and we'll import the function, or the operation, estimate quantum classifier success rate. So this is basically going to give us, so if we hand it the pile of data that I just showed you plotted, we will ask it to try and classify each one of those points, however many times that I say here, 200, and we'll give it like a starting guess, so some sort of initial bias. And it will report back, as the name implies, a success rate. So after iterating through all the data 200 times, 200 attempts each time, this initial guess gave it about 85%. So obviously this is not the most efficient classification usage here. And all I'm going to do is, now that I have that quantum subroutine, I'm going to use just a Python program that will search, use a ternary search to find what the actual angle is. So you take a range, you pick 2 points in it instead of just a binary one, and then test at those 2 points. And if we do that, you can see it goes through a number of rounds here, reports back, and this is the angle for the line that it decides at the end is likely the boundary between the classes. So it didn't do too bad. I definitely had to tweak this a little bit because the point here is not necessarily the efficiency of any of the Python side or any of that, but to just show that you can actually do the classification tasks on the quantum side. Sweet. So as a summary on that one, we can train, so if you try to scale this up, another thing that's really interesting that we know is you can train restricted Boltzmann machines faster on a quantum computer. So a restricted Boltzmann machine is basically like a neural net with only 2 layers. You have like what you would normally be your input layer, and then you have just 1 layer of hidden units. And restricted means that you don't have any interconnections between each of these layers. So this is exciting. This is also a very, very current, active area of research. So there's papers coming out about this about every week. And again, though, basically not having enough qubits is kind of a downer. And particularly in this case, also not having a formulation for QRAM. But lots of people are working on this. So as overall, what I'd like you guys to take away from this is keep it real when reading about quantum computing. Please, there's no such thing as time-traveling quantum computers. Nothing is in 2 places at the same time. We are not killing cats left and right. Please, leave the cats alone. So that's one thing. Quantum resources really do kind of necessitate changing how we think about our algorithms. You kind of got a taste of some of the both restrictions and interesting benefits that we can get from writing quantum algorithms. And honestly, like, it's something that even the research community doesn't have a super great idea about, but which kind of leads into my last point, which is quantum machine learning is really exciting, but we need you, like insert propaganda poster here. We want to get everyone involved in quantum computing and quantum programming because I really believe that it's you guys who have ideas about how you're doing machine learning, how you're doing training, inferencing, classification, everything, that will kind of be inspired by some of the stuff that the physics community has figured out, and we can work together to make a really cool new application. So there's tons of links online. I tweeted out earlier all of these links so you don't have to worry about writing them down. But thank you so much, and come talk to me more.